Okay. Good morning, guys. How did the homework go? What questions do you have? Get going. Questions from the homework. Do you guys had any difficulties with the homework? Can you hear me? Okay, that's better. So Ben is 23, 20, 73, and 67. Okay, we go through that till whenever somebody else have a question, you guys would let me know. So I'll start with number 23. What you should always have handy are the Maclaurin series of the basic functions. I will always refer to that every time we need them. So I will start looking at number 23. Okay, so here is the question. 23, we have the function f of x equal e to the 2x, and they want us to do the following. They want us to find the Taylor series, and they want us to find the Taylor series at a equal to 2. Okay, so we need to find the Taylor series of this function at a equal to 2. So I will always write it in front of me just to remind you all the time how this is Taylor series is. So it's the value of the function at 2, because that's my base point, plus the derivative at 2. So this is the derivative at this specific point, x minus 2, plus the second derivative at 2 over 2 factorial, x minus 2 squared, plus again over and over the third derivative at 2 over 3 factorial, x minus 2 to the power 3, plus so on and so forth. Okay, so really finding this Taylor series really boils down to compute all those derivatives and then evaluate them at the point 2. Be very careful. We have to evaluate them at 2. This is not an x in here. All right. They give us basically an easy function. Otherwise, it will be really hard to deal with it. So let us start working our way. So f of x is e to the 2x. So this is going to give me immediately f of 2. It means I plug in 2 for x is e to the 4. A minus 3, did I misread something then? Oh, yeah, my apology. I've read the problem before it. Thanks. That's the power of the eraser. It's great. So 3, 3, 3, 3, 3, 3, and 3. Okay, so now everything has to be erased. So this is going to give me the value of the function at 3e to the power 6. Very good. Now f prime. The chain rule, because I have 2x. So it's going to become e to the 2x times the derivative of the inside, which is 2. Immediately f prime at 3. So it's going to be 2 times e to the 6. And the idea, I'm going to keep basically finding derivatives till a pattern occurs. The minute I have a pattern, I stop. And we're smart enough to be able to figure the pattern in this problem. So what's the second derivative? Again, I need to use the chain rule. So I have a 2 times e to the 2x times the derivative of the inside, which is another 2. So this is going to give me 2 squared e to the 2x. So the second derivative at 3 is going to be 2 to the power 2 times e to the 6. Okay, I'm going to find the third derivative, and then the pattern will actually, of course, is going to show up. So it's going to be the third derivative, 2 to the power 2, e to the 2x times the derivative of the inside, which is 2. So the third derivative is going to be 2 to the power 3 e to the 2x. Now we evaluate it at the point of interest, which is 3. It's going to be 2 to the power 3 times e to the 6. Okay, is the pattern for the derivative clear? Yes or no? Can you see immediately? Yes. So what's going to be the derivative, let us say, of any order now? Suppose I am curious about the 10th derivative, just for the sake of it. What's going to be the 10th derivative? Clearly, it's going to be 2 to the power 10 e to the 2x. So I kept finding them because I'm after a pattern. So it means the nth derivative is at 3 is going to be 2 to the 10 e to the 6. And now, usually, eventually in the future, for those who study mathematics, they will learn how to show that the pattern holds. But for now, we're basically accepting that it's going to hold because it's clear. So now let us write this function, the Taylor series of this function. So it means that e to the 2x equal to the value at 3, e to the 6, plus the derivative, 2 derivative at 3 times x minus 3, plus the second derivative over 2 factorial. So that's my 2 factorial. My second derivative was 2 square e to the 6 times x minus 3 to the power 2. Plus, again, I'm going to go after the third derivative. The third derivative, 2 to the power 3 e to the 6 over 3 factorial to the power 3. And I guess now I write only this term, and then we're going to write it in sigma notation. X minus 3 to the power 4, and there are a lot of other terms. So in sigma notation, this is going to be sigma. Sorry, sigma. The general form is 2 to the n times e to the 6 over n factorial x minus 3 to the power n, and my n seems to go from 0 all the way to infinity. Okay? Any questions about this problem? Okay. So we're going to move on to your second questions. So I will scan what I'm doing here and put them on Blackboard as usual. So your second question was number, I do them in order. So the second question was 67. So number 67. Okay. So this is the second page. Very good. Now let's look at 67. What is it about? Okay, 67 is, sorry. All right. Use multiplication or division. I didn't cover division. I'm satisfied with multiplication of power series to find the first 3 non-zero terms in the Maclaurin series of each function. So they want us basically to multiply 2 power series, but not multiply them all the way, just get the first 3 non-zero numbers. So here is my function. So my function is e to the minus x squared times cosine x. Okay, so how do we do that? We take each one of them, each function, because they want Maclaurin. So it means they want everything based at 0. And of course, they don't want us to use the formula because it's very messy, as you guys can see. Finding derivatives of this function is really messy. So what they want us to do is the following. We're going to e to the minus x squared, I'm going to substitute this by its power series that we should know, cosine x by its power series, and basically multiply. All right, so that's what we're going to do. Cosine x, we know it. It's 1. It only involves the even power of x. So it's x squared over 2 factorial plus x4 over 4 factorial. Now, I want the first 3 terms. I think this will be enough to give me the first non-zero terms. Now, e to the minus x squared, we have to be a little bit careful with that. So e to the minus x squared, so I need e to the x. So I'm going to put e to the x in front of me, and then I'm going to substitute. That's how I will remember. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus so on and so forth. Now I want minus x squared. It means I need to plug in minus x squared in here. So it's going to give me 1. Instead of x, I have minus x squared. Instead of x squared here, I'm going to have x minus x squared squared. But since I am, it's going to give me over 2 factorial. And I don't think I need more terms because this will be enough to give me the first 3 terms. Because if we think about it, the first 3 terms are going to be the constant term, coefficient of x, if there is any, coefficient of x squared, x cubed, x4 at most. So I don't really need more than this. And now let us actually start multiplying them. I'm going to multiply up to x4 and then do it. So 1, and now I'm really multiplying term by term, exactly the same way we multiply polynomial, but I'm going to stop at x to the 4 because I only need the first 3 terms. So 1 minus x squared over 2 factorial plus x4 over 4 factorial. Now, the reason I'm stopping at x4, not x to the power 3, because it's very clear there is no x3. So I may need the x4 term. I'm going to stop after that, because after this, I'm going to multiply by x to the power 6, which we will not need. Now, then I'm going to move forward. So that's going to give me, now I'm going to distribute this piece. So this is minus x squared minus minus plus x squared times that, give me x4 over 4 factorial. Minus plus, most probably I will not need this term, x6, okay? Now, one more. Again, I'm distributing exactly, you deal with them like polynomial. I'm repeating this over and over because that's what I want you to do. So this is going to give me x4 over 2 factorial minus x6 over this time that, 4 plus 2 is a 6, 2 times 2 it's a 4. And then x8, I don't think we need it because we only need the first 3 terms. So now we are going to connect dots and proceed. So all the coefficient of x to the 4 actually are showing up now because when I multiplied 1, I multiplied up to x4. I didn't multiply what comes here because it's going to be x6 and I don't need x6. I need only first 3 terms. X to the power 2, I multiplied it by 1. I picked up the x to the power 4. After that is x to the 6, which we will not need. Again, I did that. X to the power 4 times 1, I need this. And then after that is the x6 that basically I don't need because I only want the first 3 terms. Now I'm going to collect them. X squared together, x4 together. Constant term, I only have this. I have no coefficient of x. X has disappeared for reasons because x squared give me only even power here, and the cosine is only giving me even power. So there is no odd power to work with. Now all the x squared, I'm going to combine them together. So I'm going to have this one, and I have that one. So this will give me what? Minus a half, right? And minus 1. So this will give me minus 3 over 2 x to the power 2. So if I do any mistakes, please let me know. Now I want to combine x to the 4 together. So let's see, what do I have for x to the 4? I have this plus that, I have plus this, and I have plus this. That's for x to the 4. Those, so I picked up the first term, I'm picking up the second. Now I have to pick up all the coefficient of x to the 4. So let's see, what do we have for x to the power 4? I will factor out x to the 4 and see what I have. If I factor it out, this will give me 1 over 4 factorial. This also 1 over 4 factorial, and this will give me 1 over 2 factorial. Now, plus everything after that, the power is going to be more than 4. And it's going to be x6, x6. So I don't really care about those because they don't want me to do them. Simply because what is the factorial for that part is? Which part, Philip?
3 over 2x squared. Doesn't that, the 2 in the bottom, it had a factorial before. Where did it go?
Yes, but 2 factorial is what?
Oh.
It's 1 times 2.
Yep. Okay.
Yeah. Okay. Yeah. That's fine. That's fine. That's fine. So, all right, makes sense? Sure, it does. Okay. So now, finally, I will just do the simple math. Sorry. Remind me when I am off. X to the power 2 plus, at this stage, is just common denominator and proceed. So I have 1 over 24 plus 1 over 24, give me 2 over 24. So this whole thing is going to give me 1 over 12 plus a half. So finally, I will get 1 minus 3 over 2 x squared plus 1 over 12 plus 1 half. 1 half is 6/12. I will have 1 plus 6, which is going to give me 7 over 12 x to the power 4, etc. Okay? Any questions? So now what is really going on? So here, which means that, so my function f, my original function is e to the minus x squared times cosine x, all right? And we found its Maclaurin series by basically substituting for this piece and that piece. Had we used the formula, which we will not, then the value at 0 is going to be this piece. It's going to be actually 1. And we can plug it in. E to the 0 is 1, cosine 0 is 1. What the derivative at 0 would be? What do you think the derivative at 0 will be without computing it? Can anybody answer this question? Without any computation, what do you think the derivative at 0 will be? What is the factorial for that part? Oh no, sorry, I answered this question. Yeah, what is f prime at 0? Absolutely 0. Because what is f prime of 0? How does it show up in the Taylor series or Maclaurin? It shows up as the coefficient of x. And the coefficient of x here is 0 because there is no x. It means f prime at 0 has to be equal to 0. Because had I applied the formula for Taylor, this is going to be f of 0 plus f prime at 0 times x. That will be the formula, plus the second derivative at 0 over 2 factorial x squared plus so on plus so forth. So if I use the formula, which is very hard to use in this scenario, I should have had f prime at 0 times x here. But there is no coefficient of x in this scenario. It means this should have been equal to 0. Okay, I push you a little bit more. What do you think the second derivative at 0 is? So if you basically, what you have to do is compare those two. If I had used the formula, the coefficient of x squared should be the second derivative at 0 over 2 factorial. By avoiding it, I have that. You are almost correct, not quite, Christian. I think you are off by a little bit. Yes, yes, or is right. So what is the coefficient? This tells me that f double prime over 2 factorial is the coefficient of x squared. It means f double prime of 0 over 2 factorial is the minus 3/2. Okay, so it means the second derivative at 0, if I solve for it, that's the second derivative at 0. Over 2 factorial is minus 3/2. It means this is equal to minus 3. It means if you had sat down and spent, I don't know, a few minutes to compute the second derivative of this function, then evaluated it at 0, you will get exactly minus 3. Now, what's the third derivative at 0? Okay, absolutely, it is 0 because the third derivative at 0 should come from the coefficient of x to the power 3, which we don't have right now. Okay, one more question, and then I will proceed. What's the fourth derivative at 0? This is everything in front of you. What do you think is the fourth derivative at 0? Okay, I'll give you, okay, Sarah is telling me 7. Do you agree with Sarah? That's the coefficient of x4 right there. The Taylor formula tells me that this should be equal to what? And then, are you sure, Sarah? Somehow I'm having trouble with 7. Okay, I give everybody a minute. Okay, I got a question answer from Christian. I want others. I give you a minute. I want answers. Set it up. Set it up. Set up the picture. I mean it a minute. I'm going to keep quiet for it. Okay. I have some answers. I want others. Okay, it's getting better. Okay, we're improving. All right, Zach, all right. Who would like to tell me? Somebody in mute and explain where your answer is coming from. Don't make me pick. I give you +1 on your quiz if you explain it. And I mean it. Can you speak up, Sarah? Or you don't like to? It's 24 twice. Okay. All right. So I will explain exactly. What is the f sort? The coefficient of x to the power 4 in the Maclaurin series should be the fourth derivative at 0 over 4 factorial. So if we use the formula, the coefficient of x4 should be equal to that. Now, we got 7 over 12. So it means that the fourth derivative at 0 over 4 factorial has to be 7 over 12. And now I need to solve for the fourth derivative. But 4 factorial, as your classmate is telling me, is actually 24. This is 7 over 12. So it means if you have done the work, all of it, and computed this, if we solve, so we're going to solve, we will get the fourth derivative equal to 40. So the point is that regardless how you find the Maclaurin, whether you use the formula or you use series that we know, you get exactly the same answer. It means this will always be the value of the function at 0. The coefficient of x squared will always be the second derivative at 0 divided by 2 factorial. the coefficient of x4 will be always the fourth derivative at 0 divided by 4 factorial. Regardless of how you find it, there is one answer. So we picked the easy way to do it. And in this scenario, that's the easy way to do it. Now I look at the last problem you guys asked me. And okay, so let me see, was it? Sorry, I have to back up and chat to see which is your last question. 73. Okay, so I look at 73. Okay, so let's see what 73 is about. Okay, find the sum of the series. So here the idea is start recognizing some very basic one. So it's -1 to the n x to the power 4n over n factorial. And my n here goes from 0 to infinity. Okay, and the question is we need to recognize, somehow connect dot. Does this remind us any of the basic series, the basic one? And then compute it. Okay, anybody has any idea? So whenever I have something over n factorial, it should remind us the power series or the Maclaurin series of 1. It reminds me definitely the e to the x. That's what it reminds me. So I'm going to write e to the x in front of us and then connect dots. So first of all, this is equal to, just let's write the first few terms because we see it better. I see it better when I have the first few terms in front of me. So at n equal to 0, I'm having 1. At n equal 1, I have x to the 4 over 1 factorial. And then I'm having x equal n equal to 2, x8 over 2 factorial, and then definitely over 3 factorial. And this is x to the power 4 times 3, which is 12, and so on and so forth. Okay, now I'm going to put e to the x in front of us. I'm going to put e to the x in red. And then I want you to connect dots somehow. E to the x is sigma x to the n over n factorial, n equals 0 to infinity. Okay, so this is equal to 1 plus x. I mean, writing x both places is a bit confusing, but I will. Okay. All right, so let us connect dots. Somehow they look the same, but not the same. So what is playing the role of x in this scenario? Now I let you watch. So they somehow look the same. It's 2 factorial, 3 factorial, 4 factorial, 1. But what is x in this one? What's the value? Okay, I'm getting x to the power 4. So that's one suggestion. Kind of. Okay, if I take x, no, x to the, you're almost right, Sarah, but I don't like the n in your answer. Okay, so the suggestions are, I'm taking x to the power 4. So if I follow you and I put x to the power 4, right. Now the last answers that I have on chat is the correct answer. If I put x to the power 4 here, so if I put x to the power 4 here, what this would become? X to the 4n. So you're picking up only this piece. But I have a minus. So how I'm gonna compensate for that? Which value of x? It's not gonna be x to the power 4, it's gonna be minus x to the 4. So what answer should be is we're gonna need e to the minus x over 4. So what I'm substituting is not really x to the 4, it's minus. So if I do that, what are we gonna? So I'm gonna substitute minus x to the 4. So instead of this x, I'm going to put minus x to the 4 to the power n over n factorial. And now will this do it? Yes, because minus x to 4 to power n, we can rewrite this as minus 1 to the n, x to the 4n over n factorial, n equal 0 to infinity. So my original expression here, so the answer is e to the minus x to the 4. Okay. Any other questions before we move on? Okay, so I'm gonna assign, like for tomorrow, I assigned the homework. Probably I will give you to do them again, just so you can start building a feeling of how to substitute within the system. Okay, any other question before I move on to basically the last idea in this chapter? Okay, so I will put those, I'm gonna scan this and put them on Blackboard so for you guys to see. And then we're gonna move to the last idea and the Taylor polynomial. So first I will read a little bit and then I'll start working with you. So Taylor polynomial. First, let's go back to the Taylor series. The Taylor series of a function at a point is given by this way. It's f of a plus f prime of ax minus a plus the second derivative at a over 2 factorial x minus a squared plus so on and plus so forth. What are the Taylor polynomials? The Taylor polynomial are the partial sums of the Taylor series. Means the partial sums. It means this and this and that. They are nothing more than the partial sums of the Taylor series. So let me define them now again. So what are the Taylor polynomials? Taylor polynomial of f of degree 1 centered at a is f of a plus f prime of a x minus a. So it's basically the first two terms. This piece right there. We call this Taylor polynomial of degree 1. Polynomial because this is a polynomial. There is no x to the half, there is only x to a power. Of degree 1 because the highest degree of x is 1. Now, what's the Taylor polynomial of degree 2 centered at x is you keep adding the partial sum till the degree of x is 2. So it's f of a plus f prime of a x minus a, f double prime of a 2 factorial x minus a squared. So that's the Taylor polynomial of degree 2. And in general, the Taylor polynomial of degree n at the point a is the nth partial sum. It means f of a, you keep adding up to the degree n. So to get the degree n for a polynomial, you have to take x minus a to t. Now we use Tn for Taylor polynomial because T stands for Taylor. That's where the T coming from. Some books use actually the P because P stands for polynomial. Our book is using T because T refers to Taylor. Before we start working with those polynomials that we have seen, let us talk a little bit about the graphical interpretation of at least the first degree Taylor polynomial. All right. Let us see what's the first degree Taylor polynomial. So I'm going to write this on another sheet of paper so I can explain. Okay. The first degree Taylor polynomial is the following. So I'm going to at least try to understand the first one. So the first one is T1 of x equal the value of the function at a plus the derivative times x minus a. What is this polynomial? That's a polynomial of degree 1 because that's the value of x. So if we graph this, we basically should have a line because we only have x. It's like mx plus b. So graphically, what is it? Let us think a little bit. And believe me, we've seen this a lot in 163. What this is? Let me take you back to 163. Suppose you have a function. That's a function. And this is a point on the graph. This is a point A, and this is the point F of A, point on the graph. And let me take the tangent line. The tangent line. What is the slope of the tangent line? So the tangent line at the point A, F of A. Now let us remember, what is the slope of the tangent line? The slope of the tangent line is, quickly, what's the slope of the tangent line at the point A, F of A? It's just the derivative. So it's the derivative, but not the derivative anywhere. It's the derivative at the point A. That's what the slope of the tangent line. So what's the equation of the tangent line? What's the equation? Let us remember how we find the equation. So the slope is the derivative at A. The point is A, F of A. I'm finding the derivative right there. So what is going to be the equation? The equation will be y minus F of A equal the derivative at A times x minus A. That's the equation of the tangent line. So if I move the F of A here, the equation of the tangent lines become F of A plus the derivative at A times x minus A. And now you can see the connection between those two and those two. So the first degree Taylor polynomial is nothing more than the function whose graph the tangent line. It means that this polynomial, if I graph it, is exactly the tangent line. And we know that near a point, a function looks very much like its tangent line. So that's what the first degree Taylor polynomial is, nothing more than the tangent line to the graph at the point A, F of A. And we know that the tangent line approximates the function very well. The tangent line at A approximates the function very well at A, but if I take a point right here, it doesn't approximate the function here. It approximated near the point A, F of A. And that's where the base point is going to become very important, because it approximated near this point. So total understanding of polynomial of degree 1, because it's crucial, because this is, we can really see it. It's nothing more than the tangent line. Now, polynomial of degree 2, it becomes harder to really imagine it, but I can really a little bit talk about it, so to help you a little bit. So now we have T1, the first degree Taylor polynomial, is nothing more than the tangent line. That's what the first one is. That's the first partial sum of the Taylor series. The second one is, as I said, it's harder because it's not a line anymore, but let's see at least how it looks like. That's the second one. Okay, and this is, now I'm gonna sketch here a little bit, the best I can.
So have we completed the 2018 tax return?
2018, yes.
Questions? Are you guys asking me a question or what?
1040.
No, Connor just hasn't muted himself.
Okay, so now let's go back here. This is my function. This is the point A. And this is my first degree Taylor polynomial. That's the one we understand fully. Now, the second degree, question number 1. What type of graph does it have? I will mute Connor. Okay, thanks. Now, T2, what type of graph do you expect? parabola, absolutely, because the degree is 2 here, it means the highest is x squared. So we're going to have a parabola. Now let me tell you a little bit about this parabola. The most I can tell you is the following. What's the value of at A of my second degree Taylor polynomial? What's the value at A? It means if I plug in A here, what should I get? A minus A0, A minus A0. It means its value at A is exactly the value of my function at A. So it definitely, it has to go through this point. Actually, it has other property. So if I compute its derivative at A, derivative, what do I get? This is a constant. F prime of A is a constant, that's a number. Derivative of x minus A is 1. I'm going to get F prime at A plus. This is a constant. And derivative of x minus A, this is 2 times x minus A. So the derivative of this polynomial is, those two simplify, F double prime of A times x minus A. So at the point A, and that's the piece I want to, at the point A, means if I plug in A here, the derivative of it is exactly the derivative of the function. So what's the second degree Taylor polynomial? It is a parabola. Its derivative here is the same as the derivative of the function. So it's going to have the same tangent line. And the last piece is, if I compute its second derivative, and I'll leave you the pleasure of doing it, you're going to get exactly the second derivative of the function. It means the second derivative is a question of concavity. It means if the function concave up, my parabola will be concave up. If the function is concave down, my parabola will be concave down. So the second degree Taylor polynomial is going to be like this. Have the same tangent line, it goes through the point, and it shares the concavity of the function. So it means it's going to hug the function a little bit more than the tangent line. So this is going to be T2 of x. It's going to be absolutely closer to the function than the previous one. And what we can show is the following, that if I take the third degree Taylor polynomial, it's going to be actually even closer and closer to the function. So those polynomials, those Taylor polynomials, which are the partial sums of the Taylor series, are actually going to approximate the function better and better and better. T1 will approximate a function by a line. T2 will approximate the function by a parabola, but they approximate it better than T1. T3 will approximate the function by a cubic, but better than T2, and so on and so forth. So let us do some examples to elaborate those ideas. And I hope I can have time just to show you on a graph how these things work. So I'm going to take the examples of that. So I will take the function f of x equal ln of x. Okay. And my first question is, find the Taylor polynomial of f at the point A up to degree 4. So I want the Taylor polynomial. So how do we find the Taylor polynomial? We have to find, basically, it's like finding Taylor series at 1, but I stop at the 4th degree. That's really what is going on. So let's use it verbatim. So I need to find the Taylor polynomial of degree 1 first. So the formula for degree 1 is f of a plus f prime of a x minus a to the power 1. Means I need the value of the function at 1, the derivative at 1. So we did that. I took f of x equal ln of x, f of 1, I plug in 1 here, I get 0. F prime is 1 over x, I plug in 1, I get 1. So T1 is going to be f at 1, which is 0, plus f prime at 1, which is 1 times x minus 1, which is x minus 1. Now the second degree Taylor polynomial. I need to compute the second derivative at x. Okay, now the easiest way is 1 over x, write x to the negative 1, and I compute the second derivative, which gives me x to the minus 2. And I plug it back into the formula. So I get x minus 1 minus plus the second derivative at 1, which is minus 1 over 2 factorial x minus 1 squared. I did the same for the third degree. It's x minus 1, the second derivative over 2 factorial plus the third derivative over 3 factorial. The third derivative at 1 is 2. And finally, the fourth degree Taylor polynomial. So we're just computing now, nothing deeper than that. It's again x minus 1, 1 over 2 factorial, 2 over 3 factorial, and then I have to add the fourth derivative. The fourth derivative is minus 6 over 4 factorial. Okay? So this is the fourth degree Taylor polynomial. Now I'm asking you the following. Sketch on the same screen the graph of the function and the Taylor polynomial up to 4. So I'm going to try to share screen today with you. I've never done it before, so I hope it's going to work. So I'm going to try to share the screen and show you graphically this. So, and shout if it's not working. I hope it does. I hope it does. Okay, can you guys see it? Can you see the screen, yes or no?
Yep, looks good.
Very good, great. So now this is my function ln of x. Now I still have to figure out how to do something. Okay, I think I managed. Okay, this is the function ln of x. That's the graph of ln of x. Okay, do you guys see it? Now we're gonna start sketching the Taylor polynomial. All right, I think this is better. So here, that's ln, the center is 1, and that's the degree of the Taylor polynomial. So the first degree Taylor polynomial, x minus 1. Graphically, what does it represent? So this is 1. 1 is right there. That's 1. What does the first degree Taylor polynomial represent? The tangent line. So that's what we got. So x minus 1, that's exactly the tangent line. Now the second degree Taylor, the second degree Taylor polynomial, that's the parabola I talked about. And this is the parabola that it coincides with the value of the function at 1. It has the same tangent line and it curves exactly like the function. So it's a little bit better approximation of the first one. Now n equal to 3. Sorry. Here we are. N equal to 3. You realize that the third degree Taylor polynomial, which is a cubic function, it's actually better than the previous one. It means the value of the log and the value of those polynomials are very, very close to each other. Very close. I can take n equal to 4. I can take n equal to 10. What do you realize? Are the values of the log close to the value of the polynomial? Yes or no?
Absolutely.
Now, where do they stop being close to each other? I want you to look at the picture carefully. Are they equal to each other for all values of x? Yes or no? It means I take x equal to 4. What can you say about the log and the value of the polynomial? Are they close or far apart?
Far apart.
Far apart. What about at, no, minus 2 make no sense. What about at 3? They're also, this is 3. That's the log, far apart. So when are they close to each other? First, near 1. And that's the importance of the base point. It means if you want to approximate ln by a polynomial, and you're interested in the value at 1, you have to take the Taylor polynomial at 1. If you want to approximate the log by a polynomial near 6, I have to take Taylor polynomial at 6. That's the importance of the x minus 6. That's the first remark. Remark number 2. Where does the approximation stop? According to the graph that you see, the approximation is good between 0 and 2. Am I right? After 2, things seems to break up. That is a good approximation. Even though this is hard for you to understand, but accept it from me at least. Where is the 0, 2 will come from? 0, 2 actually would be the interval of convergence of the Taylor series. It means this series, the Taylor, if I put the whole Taylor series of Ln of x and I find its interval of convergence is going to be everything between 0 and 2. It's going to be centered at 1. The radius is going to be 1, and the interval from 0 to 2. It means that the Taylor series will actually equal to my function exactly where my Taylor series converge. It means 0 and 2. After that, each one has its different way. So the equality, the approximation work within the interval of convergence of the Taylor series. And the importance of the base point is basically what I said a minute ago, is when I am close to 1, I have a great approximation, and I get farther away from 1, the approximation get a little bit bad. Between 0 and 2 is good. After that, it makes no sense whatsoever. So let us say I want to approximate Ln of x by a polynomial, but I want the approximation at 6, near 6. What should I take for base point? What should I take for A? Quickly. If I want a good approximation for Ln, I have to take A equal to 6. And now I get an approximation near 6. That's the way it works. So if you want to look at Ln of x, approximate by its polynomial at 6, then you have to take everything near 6, because that's where the approximation works. It falls apart beyond that. All right? So let me go back to myself. Also. Okay, now I have to know how to get back to the lecture. Okay, sorry guys, I forgot how, stop share. Okay, all right. Is this making sense? No. So now the last piece here is, sorry, I'll take a few more minutes, but I want to at least finish this piece. My question is, use T3 and T4 to estimate Ln at 1.5. So what do I mean by use T3 and T4? It means that, okay, those polynomials approximate the function. What I want you to do is, I want to approximate Ln at 1.5 by using the polynomial. So basically, I want you to plug in 1.5 into the expression of the polynomial and see and use it to approximate the value of the natural log at 1.5. So what I did right here is verbatim. I plugged in 1.5 in the expression of the polynomial. So I put 1.5 here. 1.5 minus 1, that's 0.5, minus 1 over 2 factorial. 1.5 minus that is 0.5 squared, plus 1 over 3, 0.5 to the power 3. So I did exactly that, and I got 0.4166. I carry on, and I went to Ln of 1.5. But I used the 4th degree Taylor polynomial. My answer was 0.4054. Now I compare it to the value that you get from a calculator. The calculator will give you 0.45460. The 4th degree Taylor polynomial gave me that much. And we can see how close they are to one another. Okay. All right, I have to stop at this point. Read the last page of my notes. I work with the exponential and do your homework for tomorrow. Okay? Any questions before I quit? Any other questions? All right. So, okay, I'll see you in my office hours. Bye-bye for now. Okay, any questions? Are we getting the test back tomorrow? No, Sarah, I am sorry, not this time. I only graded like 10 students. So it's gonna take a while. My apology this time. It's a bit tedious. No, you won't get those. Yeah, so it's a little bit tedious, this grading. I will do my best to get it maybe Friday or Saturday. Okay? Any other questions? Okay, see you tomorrow. Bye, guys.